everybody. I'm going to talk about reaction coordinate diagrams in this video. So first off, these are a couple of reaction coordinate diagrams that I have up right now. A couple things to take note of here in terms of axes. So your y-axis is always going to be energy. So higher up is higher energy, more reactive. Lower down is lower energy, less reactive. And then your x-axis is going to be called your reaction coordinate. I like to think about this as a reaction progress. So kind of like this is the reaction progressing along as it occurs. Okay. So the farther along you go, the more towards kind of product you're going. Alrighty. So let's go ahead and label some of this out. So on the left-hand side here, this little dip is our reactants. Okay, so we're seeing our reactants start off at this particular energy level. And then we're seeing them go up. And then we're getting up to our transition state. Okay, so that energy to get to the transition state is your energy of activation. And remember, EA, that's going to be energy of activation. That's going to be the amount of energy that you need to get the reaction going. Okay, and then up at the top there, this is our transition state. That's indicated by the double dagger symbol, and that is our transition state. Okay, so it's important to note that anything that gets to a transition state, like this, is not something that you can isolate. If you think about the reaction as, or the compound as a ball, that ball is either going to roll down that way or roll down that way, but it's not going to just stand there teetering at the top here. So this is a very influx type of position, okay? So we've got our energy of activation. Then the other thing that we want to look at is our delta G. Okay, delta G has everything to do with the difference in energy between your reactants and your products. And our products are this other dip over here. Okay, so we've got reactants, we've got products, we've got the delta G. And that's going to be what we're looking at here. Okay, so if our delta G, which is when we're thinking like products minus reactants, if that is negative, okay, that's going to be an exothermic reaction, a spontaneous reaction. And it's going to produce heat. Okay, you'll also hear people say spontaneous for something with a negative delta G. Okay, meaning that it just can kind of go on its own. It's going to be able to go without a lot of help. All right, so let's look at this other side. So again, we've got reactants over here on the left, and then going to products on the right. We have all the same kind of things here in terms of the energy of activation required. Okay, we've still got a delta G here. And we still have a transition state. Okay, and in this case, though, if we're looking at this minus this, that is going to be a positive number this time. So delta G is positive here. So that means that this reaction is going to be endothermic, meaning it needs heat. So you have to put heat in, some sort of energy in to allow this reaction to occur. Okay, so that's kind of the basics of this. And again, let's go ahead and write down here our delta G. And that's going to be our Gibbs free energy. Same as what you talked about in Gen Chem. And we're not going to get super deep into, you know, the math behind all of this. So we're not really going to be calculating any delta G's. What we're more concerned about and what's going to be more helpful for us is actually kind of using these diagrams to help us understand what reaction processes are occurring. So don't get too wrapped up in this, but this is something that is really helpful just to kind of have another layer of explanation here. All right, so then let's look at a couple of other terms here. So our first term is kinetics, okay? Kinetics is all about speed. This is all to do with the rate of the reaction. Okay, so if I'm looking at the rate of the reaction, this is really determined by the energy of activation. Okay, so kinetic products are going to be the fastest ones formed. Okay, so you're looking for which product is going to have the smallest energy of activation because that's going to be the quickest one to get over. Okay, so we're really looking for small EA here. Okay. All right, so then we've got thermodynamics. Kinetics and thermodynamics are often kind of rolled together into one discussion, but it's really important to keep in mind that they are like two totally different things. So kinetics is all about speed and rates, and thermodynamics is all about stability and energy. So for thermodynamics, we're really looking at the equilibrium concentration of reactants and products. Okay, so in that, we're really looking at the thermodynamic product as being the lowest energy product. Okay, so if you've got a choice between two products and, you know, one might be faster to form, but one might be more stable overall, that's kind of what you're looking at in terms of kinetics versus thermodynamics, is which one can form fastest, but which one is more stable. Okay, and we'll see that come up kind of throughout the year. So we'll be jumping back and forth to these ideas quite a few times. So if it's not quite clear right now, that's okay. At this point, we're just kind of getting used to having this incorporated into our thought processes. But like I said, it's going to come up a lot more later, and it'll kind of, you'll get the hang of it as we go. But if you're not sure right now, that's totally okay. All right, so I just kind of want to show an example of drawing out an energy diagram here, or a reaction coordinate diagram from a reaction. So I think it helps to see it kind of put together all at once. So first, this is going to be a multi-step reaction. Okay, so this is our reactants on this side, and these are the products. Okay, and then there's multiple steps in between that are required in order to get from reactants to products. So we're going to look at this as a multi-step reaction. And the first thing I want to do is just go through here and add in our arrows so that we kind of understand mechanistically what's happening. If I can get this all selected. All right, so once we're here, if we kind of look at our reactants and then to the next set, we are forming a Br minus and a carbocation. So this is going to be a leaving group leaves situation, leaving a carbocation behind, and then our bromide is left over. Then we've got a nucleophile came in, so we've got a nucleophilic attack next. Using those oxygen lone pairs, we're going to go attack that electrophilic carbocation. That's going to give us this. And then we just need more of our alcohol to do an acid-base proton transfer here and get to our final product. Okay, so what I tend to do here is I tend to label like each chunk in between the arrows. So we're really looking at these arrows as going to be kind of our guideline for where our different pieces are occurring. So if we look at this as being reactants are A, and then after the second arrow, this is going to be B, and then the third arrow is going to be C, and products are going to be D. Okay, so we're using these reaction arrows every single time you're drawing one of those. That's going to be kind of one of your stages that you're setting. So we're basically imagining kind of here, here, here. Okay, all right, so once we're there, then let's go ahead and set up our reaction coordinate diagram. I'm going to do a nice big one here. Okay, so I've got energy on the Y, reaction coordinate on the X. So, and I'm going to start here, and for when we're filling these out, I'm generally going to give you the starting and ending point, so you don't have to determine whether or not it's going to be endothermic or exothermic. I will usually give you that or tell you, make sure that you draw it as exothermic or whatever. So I'm going to just kind of tell you that this process is going to be a little exothermic. So we're going to start with A here and D here. So the important thing to keep in mind here is like each of these stages, these are intermediates. Okay, so intermediates are minimum, but they're not absolute minimums. Okay, so remember back in math class when you had a graph that was like, had some of these things and you have various low spots, that's kind of what we're looking at here, where wherever we have intermediates in between the product and the starting material, those are going to be intermediates where they're kind of minima that are there, but not the absolute minimum necessarily. All right, so let's go ahead and start here. So I need to go from these to this. Okay, I always like to think a little bit about what's the stability of that compared to that, right? Carbocations are not very stable. So we should be going up in energy pretty significantly here. So we're starting at A, and then we're going to go up to B. Okay, so that's going to be up at B. And then we've got C. Okay, so if I'm looking at a carbocation versus a positive charge on an oxygen, right, we're using all those same rules where we're saying this one doesn't have a full octet, at least this one does have a full octet. So we're going to be going down in energy, but we're still not going to be as low in energy as like a neutral molecule. So we're going to go up again a little bit, but then we're going to go down. Okay, but we're not as low as this because this is still higher energy than this guy. Just kind of using charges as your guide a little bit. Okay, and then we've got an acid-base reaction. The acid-base reactions usually are going to have a very, very small little energy of activation. And then we're going to drop on down to our product. Okay, so it's going to look something like this. I know this one looks a little bit shaky, but that's okay. If they look a little shaky, that's still fine. So then when you're looking at this, if you're trying to determine the rate determining step, okay, you're really looking at what is going to be the thing with the highest energy of activation. Because again, if we're thinking about rates, we're thinking about kinetics, we're thinking about energy of activation. So we're looking at this as being our highest energy of activation. If we're thinking about these ones as being like little bitty ones, right? So this is going to be by far the largest energy of activation as we try to go from A to B, because this is kind of the biggest change in overall stability that we're seeing, right? So this is the hardest part, and all of this is kind of a downhill journey in energy, right? Okay, so that's our energy of activation. That is also our rate determining step. Okay, at the top of each of these, so remember at the top of our energy diagrams previously, we had these labeled with the double daggers indicating transition states. Those are all the same, okay? So these are still transition states. And this is literally kind of the molecules as they are transitioning from one to the next, okay? So if we're thinking about this, we're kind of looking at that first step between A and B as something like that. Okay, and you usually put brackets on it and a little double dagger. So what it's indicating here is that we're saying that this carbon to bromine bond is in the middle of being broken. Okay, so it's not yet fully broken, it's still not fully formed. So anything that is a bond that's broken or formed is going to get that dotted line. Okay, and it's important to note that these cannot be isolated. But we can isolate our minima, okay? So anything that's an intermediate, we can isolate. Okay, so intermediates are our minima, transition states, those are going to be our maxima. Okay, so the peaks are transition states, the valleys are intermediates. Okay. Okay. Those are intermediates. Okay, and then as we mentioned at the beginning, this overall is exothermic. And again, when we're looking at that, we're specifically looking at the difference between orange, A and D. And that's our delta G, okay? Because our A is higher than our D is. All right, so we're gonna spend time practicing these as we start getting into reactions. As always, let me know if you have any questions, and we'll see you all later.